Key to a quantum theory of gravity, a deeper theory of how reality, space, and time work. Black holes are interesting because we have a place called the event horizon where we think we have full control of the physics we understand. However, there is a fundamental clash between our two basic theories of nature, quantum theory and general relativity. The quest to unify these two great pillars of 20th and 21st century physics into what is often referred to as a quantum theory of gravity is, in some sense, the holy grail for theoretical physicists. Black holes are forcing us into a deeper understanding of what space and time are, and in that sense I think it is fair to say that black holes are the keys to understanding the universe. I'm Brian Cox. I am a professor of particle physics at the University of Manchester and the Royal Society Professor for Public Engagement in Science. Amongst other things, I am the author of the book Black Holes, The Key to Understanding the Universe. The idea of black holes goes back a long way, actually back into the 1780s and 1790s. There were two physicists, mathematicians or natural philosophers, whatever you want to call them, working at the time who had the same idea, apparently independently of each other. One was a clergyman called Mitchell, and the other was the great French mathematician Laplace. They were both thinking in terms of an idea called escape velocity. Escape velocity is the speed you have to travel to completely escape the gravitational pull of something, a planet or a star for example. The escape velocity from the surface of the Earth is around 8 kilometers per second. If you consider a more massive object like the Sun, the escape velocity is somewhere in the region of 400 kilometers per second. The escape velocity increases because the gravitational pull at the surface increases. What Mitchell and Laplace thought, and I think it's a very beautiful idea, is that they imagined in their minds, can you go bigger? Can you imagine more and more massive stars, giant stars, such that the gravitational pull is so large at the surface that the escape velocity exceeds the speed of light? If that were the case, you wouldn't be able to see them. What a black hole looks like. To understand why black holes cause so many conceptual problems, it might be worth briefly describing what a black hole looks like from the outside. There is an event horizon surrounding the black hole, which in some sense defines the boundary between the external universe and the interior of the black hole. If you cross this boundary into the interior, even if you can travel at the speed of light, you cannot escape the gravitational pull of the black hole. Another description of the event horizon, which has confused people throughout the history of black hole research, is the idea that when viewed from the outside, the event horizon is a place in space where time stops. This is a direct prediction of Einstein's theory of relativity. There is a central problem though which is still unsolved. What lies at the center of a black hole, the singularity? You might think of it as an infinitely dense point to which a massive star collapses. However, it's not entirely correct to talk about the center of a black hole, even in pure general relativity. When you look at a black hole using a Penrose diagram, named after Roger Penrose, you see that space and time are so distorted that, in some sense, their roles swap. The singularity is not really a place in space at all, it is a moment in time. It is the end of time. But the nature of that singularity was not understood, and is still not understood. For many years, people thought we had no access to it, no conceptual tools to explore it. It seemed that the singularity might remain a mystery for a century to come. Hawking radiation. The great revolution in black hole research was the realization that conceptual problems exist not only at the singularity but also at the horizon. What Stephen Hawking showed in a landmark couple of papers is that if you consider quantum mechanics in the vicinity of the event horizon, black holes actually glow. They produce particles. They have a temperature. This thing that Einstein's theory pictured as pure geometry, just distorted space and time, actually emits particles. This phenomenon is called Hawking radiation. In his 1974 paper, Hawking provided a hand-wavy description to help visualize what's happening. The idea is that in the vicinity of the event horizon, pairs of entangled particles are constantly coming in and out of existence. Sometimes one of these particles falls inside the event horizon while the other escapes into the universe, removing energy from the black hole as it goes. This means that the black hole is shrinking and eventually, it will disappear. The black hole information paradox. This discovery had profound implications. Black holes are not eternal prisons. They have a lifetime and one day whatever was inside them is returned to the universe. This raised a central question. What happens to all the information about the stuff that fell in? According to Einstein's theory, everything that enters a black hole ends up at the singularity, whatever that is. But when the black hole eventually disappears, the only thing left is Hawking radiation. The crucial question is it possible that all the information about everything that ever fell into the black hole is encoded in that radiation? This might seem like an odd question, but it is a critical one. In physics, information is believed to be conserved. Every fundamental law of nature we know says that information is never lost. For example, if I take a book and burn it, every quantum of radiation, every photon, and every particle that was part of the book still exists. In principle, if I could collect all of them, I could reconstruct the book. The problem was that quantum mechanics and general relativity, when combined, seem to suggest that black holes erase information from the universe. This paradox became known as the black hole information paradox. The quantum theory of gravity. Fast forward to today, and researchers are still writing papers on this subject. However, the general consensus now is that black holes do not erase information. We now believe that if you could collect all the radiation a black hole emits over its entire lifetime, you could, in principle, reconstruct everything that ever fell in. The implications of this are profound. It suggests that space and time are not fundamental. One emerging view, though still highly debated, is that space and time themselves emerge from quantum entanglement. We do not yet know what the fundamental building blocks of reality are, but black holes provide a glimpse into a deeper theory of gravity. To understand the origin of the universe, or even to ask questions like, did the universe have a beginning in time, we first need to understand what space and time are. Black holes, as real objects in nature, force us to confront these questions. Einstein once said that if you examine nature carefully, pulling at the intellectual threads and persistently exploring, you might catch a glimpse of something deeply hidden. That is the beauty of theoretical physics, a glimpse into the deep underlying structure of reality itself. No one knows exactly where this journey is going, but the hints of something deeply hidden continue to inspire us.